to review. All right, here we go. All right, first of all, I want to show you that I have put this paper up there, if not 5, I'll say 4, absolutely for sure, 4 times. Yes.
Did we learn Newton's second law, or am I just blanking?
Okay.
Inertia.
No, wait. You know what? I've never even asked you to tell me which one's first, second, and third. If you say you knew all 3, I'm okay, all 3. Number 1 had to do with inertia, which was mainly made by Galileo. Number 2, that was that whole last chapter, F equals ma. Now, F equals ma, we also did projectile motion with that last test, and so it was F equals ma plus projectile motion, and so F equals ma is Newton's second law. Now, Newton's third law, here we go. So anyway, let's go here. I did this with the other class, and it's interesting. If you don't break these rules here tomorrow when you take the test, you'll be in pretty good shape. Let's take a look at the first one. It says for every action there's an equal opposite reaction, but what does that really mean? It says that objects don't act on other objects. I don't hit the table. But the table and my hand hit each other. That's what Newton said. There's no delay. Objects don't act on objects. They interact with each other. Yes?
So would, like, the net force of the universe be 0?
Yeah.
Okay.
Now, if I were a theoretical physicist, that would be something interesting to try to speculate on. Could there be anywhere in the universe where monoforces were created? And if there was, then the net force would be in that direction. That's good thinking. I'm not a theoretical physicist. Next. Yes.
Yeah.
So this might be a stupid question. Why is some objects bounce so much higher than others do? Like if they have the same mass.
Wait, Clay. Why do some objects bounce higher?
Why do some materials bounce back so much?
Even though I don't want to get too far off the topic, when people make different materials, they're engineers. They're called material engineers. And I know somebody who knew about 80 different kinds of cement. He knew 80 different ways of making cement. If you live in this kind of climate, you have this kind. Anyway, that's how specific they can get. There are people, chemical engineers, that know about materials. They try to make materials. Are there people who try to make materials that are elastic? What is the theory about elasticity? Why are some objects, when you squeeze them, why do they want to tend to come back to their original shape, and others, they don't? So that's a whole other engineering thing about materials engineering. Now your original question had to do with why do some bounce back and some don't?
Like bounce back more.
I can tell you right now it has to do with bonding, but I'm not an engineer, so I wouldn't know what is it about the bonding in rubber that makes it different than the bonding in glass.
But does it have to do with this at all, or is it not?
No, that one, if it's elastic, what happens is you stretch the bonds and then they push back. So you store energy, it's called potential energy when you bend it, and then it releases back into kinetic energy like that. Tennis rackets do that. A tennis racket hits a ball, the ball actually flattens quite a bit. If you've ever seen a slow-mo picture of a tennis ball, it's actually very flat when it gets hit. And so it's storing energy, and then it comes back and releases energy, kinetic energy like that. These are great questions. I'm going to move on if you don't mind, because I want to get to some of this stuff. 2, an action-reaction pair of forces never cancel each other out because they don't act on the same object. That's kind of important that you understand that. Down here, this drawing, those are action-reaction pairs, aren't they? And they can't cancel each other out because one of them's acting on the nail and one's acting on the hammer, right? Now, don't get misled. Can any force be canceled? Yes, by another force, right? But if you're part of the same action-reaction pair, you can never cancel each other out, can you? They never act on the same object. Number 3, an action-reaction pair of forces always fit the recipe. If A pushes B, then B pushes A in the other direction, doesn't it? And they always fit that recipe. Next, this is the one you're going to have the most trouble with, and I've said this 3 times now. 2 objects can have equal forces acting on them, magnitude-wise, but they have different results. Why? one of the questions I asked on the test, give 2 reasons why equal magnitude forces can have different effects on objects. What's one?
The masses of the objects are different.
So therefore, you have to know Newton's second law to completely understand Newton's third law. What's another one?
One object is accelerated or greater than the other.
Why? Well, why though?
As with her speed.
Why would the effect, one of the effects could be acceleration. He said if their masses were different, the acceleration would be different. That's one. What's another thing that would make the effect different? Like, look what happens here. What happens to the nail? What effect did the force A1 have on the motion of the nail? Go ahead and do that one, David.
It's accelerated downward.
Yes. What effect did A2 have on the motion of the hammer?
It slows it down.
To decelerate the hammer, right? Isn't that right? So one effect would be one of them was sitting still and one wasn't. One was already moving, right? And that can make the effect look different. Which one's greater, the effect, the force of a windshield on a bug or the force of a bug on a windshield? Which force is greater? And you better say they have to be the same. Now you don't like it because what's the effect on the bug, on the bug's motion? And I can tell you right now, the acceleration on that bug, or the deceleration on that bug, was so great that even its own body shape could not maintain its integrity. And it went like that. But what was the effect of that force on the deceleration of the car? It wasn't very small. Why? And again, both objects were moving, weren't they? But deceleration on one was huge because of Newton's second law, and the other one was very, very tiny because of Newton's second law. All right, next. Draw force diagrams or label an action-reaction pair as C1, C2, for example. Make sure that the tail of each vector is on the object that it acts on, not the object that created the force. Okay. So if you see a diagram tomorrow on the test and it's a force diagram, like for example here, see that nail? It's on the nail, isn't it? If I say identify A1, don't say the word nail first. What are you going to say here? Identify A1. What do you think? Avery, you know. Identify A1. One more time.
Hammer pushes the nail down.
That's it. All right? See that? So I know it's kind of back. It seems a little backwards to you, but that's how you do that. All right. Well, I'm going to stop that, and now I'm going to review what we saw yesterday. And these are some small parts of the test. Okay, these are small parts of the test. All right, Newton. Let's go here. This picture here. This is classic physics right here. This is, matter of fact, one of the things you would learn if you studied Newton was this thing called the apple and the moon. The apple and the moon. Okay. So we know from another chapter that when an apple comes off the stem, not counting air resistance, what does the apple's weight do to it? What does that force do to the motion of that apple? Accelerate it, all right, at 9.8 meters per second squared. Is that correct? We also know that it would take about 1 second to fall 5 meters. We know that. Now, what about Newton said, is it possible that if the Earth is accelerating the apple toward the Earth, is it possible that the Earth is reaching all the way out to the moon and saying, I want you to fall. I want you to fall toward the Earth. Can the Earth's gravity cause the moon to fall?
Yes.
And the answer was yes. And he did all the mathematics to show it. And so here's the picture that I'd like you to know. This is the same reason that astronauts, they're falling, but they're not getting any closer. That's the good news. What would the moon be doing if the Earth were not here? It'd be going off in a straight line at a constant speed, right? Because of inertia. We should find you there 1 second later, but we don't. We find you there. Why? Because I'm a projectile, right? I'm kind of like a projectile that I was falling. What does a free throw do with the Earth's not here? It goes off in a straight line at a constant speed. What does a free throw do? Because the Earth is here, it falls. It falls the whole time, doesn't it? It falls away from what? It falls away from where it would have been of its inertia, right? Now, so what he did is he, and I can't believe that somebody his age did that, but he knew some numbers that some people long ago, the Greeks knew this. We knew that the apple is about 1 Earth radius away from the center of gravity. And that kind of force can cause the apple to accelerate by a huge amount. But what happened, how far away is the moon? And we knew that it was about 30 Earth diameters or 60 Earth radii. So that 60 Earth radius is 60 times further away. So what do you think? What happens to the force of attraction? What happens to the force of attraction as the distance gets 60 times greater? And another way of saying that is, look at Newton's universal law of gravitation. Any two particles in the universe, if you know their masses and the distance of their centers, you can figure out the force of attraction. It could be the sun and the earth. It could be the earth and the moon. It could be one atom of hydrogen and one atom of hydrogen this far apart. And this equation works. And I can't even believe that a human being could figure out universal gravitation. But what he found out was that the force of attraction is directly proportional to the masses. Is that right? Is that correct? So if you only double one mass, you'll double the force of attraction. What if you double both masses? Then it'd be 4 times greater, wouldn't it? And sometimes books say the force of attraction is directly proportional to the product of the masses. I get it. Think about that as one number. I get it. But how is force and distance related? And if I don't take it out of the equation, you still do it. I mean, if I don't put it on the other side, you can do that. But how is distance related to force of attraction? What would you call that? If this is all constant, how would you say, how is D related to F here? Yes?
Inverse square.
Inverse square proportionality. So one more time. The apple's 1 Earth radius away. The moon is 60 Earth radiuses away. Newton says the force of attraction should be what? The same? 1/60th? Or what else? I need you to kind of look at me. What did he say? If you're 60 times further away, the force of attraction will drop to not 1/60th, but what? 1/60 squared. Isn't that right? 1/60 squared. It drops off quite a bit, doesn't it? Now, of course, the masses have a lot to do with it too. But anyway, so it's called an inverse square proportionality. And what he did, he calculated that. He said, right here, therefore, the moon, the earth, the apple can fall 5 meters in 1 second. How far does the moon fall toward the earth every second? And it's an incredibly small amount, 1/20th of an inch or 1.4 millimeters. So about like that. Now, please don't get scared. I said the moon is falling toward the earth, but it's not getting any closer. It's falling away from what? It's falling away from where it would have been, what, if there was no gravity, right? So it's falling away from a straight line, isn't it? And when it gets here, it falls away from that straight line. And so this thing's in orbit, isn't it? It's in orbit. Now, that's exactly what's happening to astronauts. Let's talk about that and review that a little bit. Way back here. Oh, I know. We had a little fun with this. Right now, if you're on the Earth, every bit of the Earth, over there, everything's pulling on me. Everything. But all those vectors combine as if only one force is acting on me toward the center of the Earth, right? The center of gravity. But what if I were to go down in the Earth and go down like 1/3 or 1/4 of the way down in there? I'd have only this much of the Earth pulling me that way, but then I have another part of the Earth pulling me that way. So what would happen, acceleration would be really high here when I first dropped in the hole, 9.8 meters per second squared, but it'd be less than that, less than little g here. And what happens if I get in the very middle? Then I have the Earth pulling me this way, that way, that way, that way, that way, that way, and I essentially would be weightless. Okay, I think that's kind of interesting myself, kind of interesting to think about. Anyway, what about this? What about this weightlessness? And a matter of fact, if you read any good books, they don't ever say weightlessness. I guess this one did. But they always do what?
So this isn't a good
They put in, well, that's a good question. I think it is a good book. And so, many times he does put quotes around it, but I guess when he put the title, he didn't want to put little quotes. So when they say weightless here, it's in quotes, isn't it? And I even offer an extra credit project. Again, if you want to take a bathroom scale and elevator and try these different things. And again, the bigger the building, the faster the elevator. So you might get a little more dramatic results. If it's only a 2-story building, I'm not sure. You might still get results. But anyway, what happens here is if you're in an elevator and not kind air resistance and you're in free fall, if you're in free fall, what would happen is you'd feel funny, number one, and you look around you and you don't feel like you're falling, but you are falling. If you took a pen out and went like this and let go of the pen would sit right there as if it was floating. If you were staying on bathroom scales, you would weigh nothing. It would look like you weigh nothing because you and the bathroom scales are both doing this. That means you can't push on the bathroom scales. So it would look like you weigh nothing. The bathroom scale said you weigh nothing. And so you appear to have no weight. But why are you going to die? Because of your weight. Isn't that right? Your weight's what's causing you to accelerate downward, isn't it? I didn't have time to do it today, but if you want to go home, get a styrofoam cup. And what you do is you poke some holes in it. Maybe 3, okay? And you get up on a ladder, and you, first of all, you cover up the holes first, and you fill this with water. Maybe you have a piece of tape. And then you take the tape off, and the water starts coming out of the holes, right? Well, then you drop the cup. What happens? What happens if you drop the cup? When I first started it, the water is coming out the holes. What happens if I drop the cup? It doesn't. The water will not come out. Not till it hits the ground. Well, anyway, so this is one form of weightlessness, but it's really like the astronauts. This person's falling toward the Earth, and they're in a, quote, weightless environment. Sometimes they call it 0G. Sometimes they call it microgravity. Well, what are the astronauts doing? They're falling. They're falling. They're in free fall. But what's the difference between this person who's going to die and the astronauts who are not going to die? What's the difference?
The astronauts are moving so fast that by the time...
Which way?
Around the Earth.
Well, they are moving fast around the Earth, but what else? This person's moving fast down to the Earth.
They're moving fast horizontally.
They are.
Fast enough to...
So they're moving very fast horizontally, aren't they? If I put rockets on this elevator, when the elevator started to fall, and I got it going really fast that way, then they wouldn't die, maybe. You say, why not? And that's where that last picture comes in play. Now, this picture is a little different than the one I showed you yesterday, and I think some people like this picture better. But here's a woman. She takes a rock and drops it. Next, she takes a rock and throws it like that. And it spends the same amount of time in the air, but it falls further away from her, doesn't it? Then this time she throws it faster this way. And it still spends the same amount of time in the air, but look at the shape of her projectile's path. See how it's getting flatter and flatter? It's not just like this. It's not perpendicular to the ground. So what would happen if you threw it fast enough and no air resistance? If you threw it fast enough, what if the curvature of your projectile matched the curvature of the Earth? Then even Newton, back then, in the early 1700s, said, you would be in orbit. You would keep moving. Now, your inertia is keeping you moving this way, right, horizontally? And you are falling away from a straight line, so you're falling. So you're in free fall the whole time, and that's why it seems like you're weightless. And they actually feel funny. They have to get used to that funny feeling, like you ever go to Carowinds or something, and some of the rides are in free fall, and you'll feel funny, don't you, in their stomach? You have to get used to that. There's astronauts are feeling it all the time. They're feeling it all the time because they're falling. And I like this diagram here because is it a coincidence that the drawing says 5 meters here? What's that mean?
That's how far something falls in 1 second.
in 1 second. If you drop that ball, 1 second later, hit the ground, right? Now you go like this, 1 second later, hits the ground, but look where it's at. 1 second later, hits the ground, but it's here. 1 second later, it's here, it's at. And what happens if you keep throwing it and keep throwing it faster and faster and faster, then the curvature of your projectile will match the curvature of the Earth. And the number I didn't give you yesterday was this one. Well, how fast is that? How fast do you have to move horizontally to be in orbit? Even Newton understood you're not going to be in orbit right here. You're not going to be in orbit 100 feet in the air, okay? He knew that kind of speed, you'd burn up. You would burn up in the Earth's atmosphere. But if you could get above the atmosphere, and that's what NASA does. If you get above the atmosphere and you go this fast right here, if you'll go 8,000 meters per second, which is 8 kilometers per second, if you'll go 8 kilometers per second when you're up there, about 100 miles up, then here's what's going to happen. You're going to be in orbit. And why? Because the curvature of the Earth is, for every 8,000 meters you go that way, if you go 8 kilometers that way, and I had a laser beam, and somebody else said, hey, that laser beam is, it's not hitting my head. If somebody else was 8 kilometers away, the laser beam wouldn't hit them in the head. It'd be above their head by 5 meters. And so what happens is the Earth goes this far, 8,000 meters, and drops 5 meters. And why is that important? Because if you can go 8,000 meters per second, when it's time to hit the Earth would have curved out from underneath you, and you're not going to hit the Earth, and you would be in orbit. Yes?
So is it true to assume that the farther away from the Earth your orbit is, the less speed you have to keep in orbit?
Okay. I could get into that today. Can I give you at least one question? I'll give you. Okay. If you have a low orbit, like Space Shuttle, Skylab, that's in kind of a low orbit, about 100 miles, something like that, you will circle the Earth once every 90 minutes. That's not bad. You get to see a sunrise and a sunset every 90 minutes. But we have some other kind of satellites that we park not 100 miles up, but 23,000 miles up. Why? Why would you want to do that? Anybody know? Why do we have satellites that are 23,000 miles up? See, in low orbit goes around the Earth, 90 minutes. Oh, I see a different part of the Earth. I see a different part of the Earth every second. I see a different part of the Earth. What happens if you put them up here? Here's the Earth. Ready? Wait. Wait. Here we go. Oh, what's that? That's a spy satellite. You can have a geosynchronous orbit, and there your speed matches the rotational speed of the Earth, and then you can watch one part of the planet 24 hours a day. And CIA, NSA, they have control of those satellites. Of course, the president can ask them to do things. And if they want to move it, it takes a little time. They move it to one place to another. I want to watch China. I want to watch Moscow. Whatever I want to watch, they can watch and see all kinds of things. They have infrared. They have some pretty neat stuff there. So I don't want to get too much into other kinds of orbits, but there's a geostationary orbit, a geosynchronous sometimes we call it. And that would be actually a higher speed. But and there's two kinds of speed. Have you guys done rotational stuff in your classes? Did you ever talk about rotational speed versus this linear speed? Like for example, let's have a record. Here's inside the record. Here's the outside of the record. Who's moving faster? The outside, because you're going a further distance in the same amount of time, aren't you? That's your rotational speed. But who makes more revolutions per minute? They make the same amount of revolutions, right? I went around once. So I have to be careful about when I'm talking about. Okay, I'm gonna move. If you don't mind, I'm gonna leave that. It's pretty neat. That's neat to talk about. Okay, so that's all there. Now, the last thing I'm gonna do is I've given you a handout sheet yesterday, and I want to talk about very, very briefly a few things that go along with this chapter. And let's take a look at the first one. Rocket engines. It says the rocket is the simplest and most powerful kind of heat engine. It burns fuel in a combustion chamber with an open end. The hot gases produced expand greatly and rush from the open end. Actually, they rush toward the open end, then out at high speeds. The rocket moves forward by action and reaction. As the gases exert a powerful force on the chamber walls. Anyway, it says rockets can work in space because unlike other heat engines, they do not require air from the environment. For combustion. So, if you're going to make, how many of you have ever launched a bottle rocket? Good. Okay. Did you actually put it in a bottle or not? Did you put it in a 2-liter bottle or what? Okay. Anyway, the only reason I have you do that is because if you don't, it might quickly take off in the wrong direction and hurt somebody. But most of the time, if it gets started in the right direction, it'll keep going sort of in that direction. So they call them bottle rockets. But what they have is they have chemicals in here, and you light it, and then a chemical reaction takes place. The gases expand greatly and push against the combustion chamber wall, and they start pushing, the combustion chamber wall pushes the gases toward the opening, and that makes the rocket go in the opposite direction. Now, even though I wanted you to know, and the Chinese made these rockets a few thousand years ago. They knew how to make rockets a long, long time before we did. This one here is the big boy and girl rocket world, okay? I want more reactions per second. This kind of a chamber is like this. This kind of a chamber is like a cylinder. And the reaction takes place on the surface area of the cylinder. I got it. But what could I do in that same amount of space to increase the surface area? It says you can make a star-like channel. And so what we'll do is I made, this is about 3/4 of a piece of regular paper. 3/4 of a piece of paper of surface area. This is a whole piece of legal paper. About twice the surface area. And if I fold it, I put it in there for the same amount of space, I can get more power, more chemistry per second because I've increased the surface area. So if you read that and they talk about star-shaped channel, that's what they're talking about there, to increase the surface area and get more reaction per second. Now, the reason I want to show you about solid rocket engines is that even though, it was sad for me to know that it sounds kind of dumb to me. The United States stopped funding the space shuttle program. That sounded really weird to me because China was pouring huge amounts of money into their space program. And Russia was too. So I just didn't understand why you would abandon the program. Now, at this point, what was happening is some private people were figuring out that used to be you had to have a lot of money to do a rocket program, like a government type of money. Well, these people had a lot of money. And so some of them started their own space program. The European nations didn't have enough money, but they put a lot of their money together and formed the European Space Agency. See that? And now there are many places around the earth where people want to get into the business of going to space. Anyway, I did want to show you the last time. This may be the last time I even teach the space shuttle because they're going to replace it with something. I don't know if it's like it or not, but this will be the last time I'll try to teach it. How many of you ever saw a space? Are you guys still too young to have ever seen a space shuttle launch? You did see one? Okay, so I can still teach it. So here's what they did. I saw one launch. No, I didn't have the VIP tickets. I was out on the side of the road and I watched it. Did anybody else see one? A launch? Oh, good. Wow. You did? Did you have the tickets and everything? Get closer? Oh, I didn't either. Okay. Well, anyway, so here's there are 4 main parts of this STS system. Now, the STS is the Shuttle Transport System, so the whole thing's called STS. Okay. Now, let me name these parts here. These 2 parts right here are what I just talked about. Those are solid fuel rockets. They're like great big bottle rockets, okay? Very expensive. I shouldn't say very expensive. They're only expensive compared to bottle rockets. They're very cheap to make. And they provide a huge amount of power. Huge. And so this is SRB. SRB is solid rocket booster, and this is another SRB. And anyway, so what happens is they're great because they're kind of cheap to make and they're powerful, but they do have a drawback. anybody here in this class know what's the drawback? You do know? You read about this? What is it?
I would assume is that you can't reuse them.
Say it again.
I would assume is that you can't reuse them.
We actually do. They actually do reuse them. I was shocked though when I saw Elon Musk. We would let them burn out. They drop off in the ocean. We have a special ship go pick them up, and they actually would reuse them. But then here's Elon Musk, and I said, why wouldn't NASA have done this? Elon Musk, his two boosters, they had enough fuel left in them. What do they do?
It flew back to their.
They land themselves on a platform upright. Okay, come and get me. It's just amazing when I saw that. Why didn't we think about that before? But we do reuse them. But what's the big drawback about solid fuel? Yeah,
You can't turn them off.
that's right. If you like these fuses, if you start them, you're going somewhere. You cannot control them. They just burn and they accelerate you like crazy. But you can't say, hey, slow it down. No. It's turned off. No. So we use it to accelerate, and that's one way that the space shuttle system gets up into the air. Now, another thing is, see this part here? This is called the axial orbiter. A lot of people like to call it the shuttle. It's called the orbiter. This is where the astronauts are. There's a big door here, a big cargo bay, and you can put things in it. You can take things out of it, satellites, stuff like that. And it has 3 big engines. Here, big engine here, solid fuel. Big engine, solid fuel. Liquid fuel, liquid fuel, liquid fuel. See that? Now, where is the liquid fuel at?
In the big old tank.
In the big old thing. The external tank, and I'll show you a picture of the external tank. It looks like this. And so they use a fairly common fuel. The fuel they're going to use is hydrogen. And the oxidizing agent is oxygen. I get it. LOX means liquid oxygen, so you put a lot of oxygen in there. And what's interesting is you have some pumps, and you said, I want this much hydrogen, I want this much oxygen, put them in the combustion chamber. All right, here we go. And then if you want, later on, if you said, let's have less, okay, you turn it down, you can control it. Now, all this gets burned up, and it drops off also, I should say, all the fuel gets burned up. And then there's still liquid fuel in the orbiter. And the liquid fuel in the orbiter, besides the 3 big liquid fuel engines, it has over 20 little ones, little rocket engines on that space shuttle, on the wing, here. And it can do almost anything you want it to. Ready? You want to go this? Turn around. And it can go any direction at once. Now, I think that's kind of neat that they did design that. Here's a picture that this happens to be Nick Holmes. Nick Holmes, he was really into this. He actually showed me this before I saw it at all. This is what Elon Musk did. He's called a Falcon Heavy. And what he did is he decided not to use solid fuel, so all of his are liquid fuel engines. I also saw a picture here. This is the European Space Agency. They did use solid fuel and liquid fuel, so it's sort of like the way we did the space shuttle. I'm not asking you to memorize all that, but it is kind of neat to look at it. What I find out now is that here's what's happened to the space program real quickly. Elon Musk they're actually launching all the time. I was out, I know you don't do this, but I was out the other night. I happen to have a little app on my phone, and it'll say, find such and such, okay? Or I'll point it to somewhere, and I saw something go across the sky, and I could tell it was not blinking. And I happened to see it, and it was not blinking. So I pointed my phone at it, and it told me it was one of Elon Musk's rockets. And so there are things going on that you don't know about, and they're out there. And you can actually watch them if you want to. So where was that? Okay. What was I getting ready to say? So what's happening is satellites used to be big. They're like 1 ton, 1.5 tons, you know? And they had to, once they got in space, you're okay, but that was a lot of mass. But now what they're doing, they're sending out smaller rockets, and the satellites are much smaller. So now a rocket can go up and send up 8 satellites, a small rocket. And that's the world you're going to be in. Lots of little rockets sending up little satellites. Now, it is going to cause a problem. The more things that are in orbit around the Earth, you got to start tracking them, and we do track them. Now, if the small things spiral in and decay and burn up, I'm okay with that because nobody's going to get hurt. On the other hand, if I'm an astronaut out there and somebody hasn't keep track of things, could I be sitting there going this way and a satellite be going this way and just tear me in half? Yes. Could a little piece of metal cut me in half? Yes. So it's getting a lot more dangerous to be an astronaut now. Did you ever watch did you watch a movie called Gravity? What do you think about that? I was going to say, whoa, who wants to go up there? You know, I thought I wanted to be an astronaut. Well, I don't know about that. That thing ripped through atoms, didn't it? It ripped right through everything. Okay, so what we're going to do now, the rest of the period, I'm going to go back to the end of chapter 4. We'll go down the row. I'll ask you guys to answer the question, and we'll try to do them as fast as we can. And we'll try to get as many as we can done. Okay, Nate, we'll start with you. We'll go right down the row. And you can actually look up here, or you can get your own book out. All right, Nate, can an action force exist without a reaction force? No, they can't. Maggie, when a hammer exerts a force on a nail, how does this amount of force, the magnitude, compare to that of the nail and the hammer? They have to be. These are easy, right, so far? When you walk, Clay, you're next. When you walk on a floor, what pushes you along? Clay, we're going down the row.
Sorry.
When you walk on the floor, what pushes you along? It does. You push the floor backwards, the floor pushes you forward. 4. State Newton's third law of motion. Okay, very good. Back up here. Ian, ready? When you, where am I at? Uh-oh. Consider hitting a baseball with a bat. If we call the force of the bat against the ball the action force, identify the reaction force.
The ball decelerating the bat.
Okay, so if the bat pushes the ball that way, the bat does what?
Decelerate.
The ball does what? I'm sorry.
Oh, it pushes against
Pushes the bat that way, doesn't it?
So it decelerates it.
Yes. Yeah, okay. All right. Next. 6. McKinley. If a bat hits a ball with a 1,000 newtons of force, can the ball exert less than 1,000 newtons of force on the bat?
No.
What? Yes or no?
No.
No. How about more? No. Okay, next. David. If the world pulls you downward, what is the reaction force?
Against the chair.
Okay.
The chair will push you upwards.
Pull, right? So if the earth pulls me down, earth what? I do what?
Push up.
I pull the earth up. Again, you don't like that because you think the effect should be the same, but the mass of the earth is so huge, you'll never see the earth accelerate up toward me, even though it does. Yes?
Say you were standing next to a insanely massive object,
Uh-huh.
drop something.
Is the earth still here?
Yeah.
Okay.
I'm saying the insanely massive object.
What would happen is, just like when I drive my car in the mountains, let's say I've been to the Rocky Mountains, okay? If you drive your car in these huge mountains, does my car go, does it get pulled toward the mountains? No, because all the forces on you act as if only a single force acts on you. So a big massive object next to me and the earth is still here, I'd have to have all the net force. Now, is it possible if it was massive enough? Let's say the moon was sitting here and I went like that. Is it possible it might go? Oh, yeah. It's possible it could go not straight down. Now, that's a good question. Yes? One more time. Yes, Okay, let's go on. Yes?
Back to Clay's question, even if you, since the Earth is this circle, and drop it, the net force is down. Wouldn't you putting a mountain or big object beside it make the net force actually go to the right when it's added up?
Even if like.
What would happen is,
'Cause
if
if
you
the
took
net force
the
already goes
center of gravity of the Earth and the Moon, they would together have a new center of gravity combined, and this thing would fall toward the new center of gravity.
Okay.
We have planets that circle the Earth, but you know what really happens? The Moon goes around the Earth, doesn't it? Do you know that the Earth doesn't really sit still? The Moon and the Earth are both kind of circling around the center of their gravity. We have things called binary stars where they go like this. They both circle, they go around and they go like this. And so they actually rotate around the center of the gravity of both of them because their masses are almost identical. So there's a lot of neat things that astronomers have figured out using physics. Let's go to the next one. 8, where did I leave off? All right. When a cannonball is fired, are the forces on the cannonball and on the cannon equal in magnitude?
Yes,
Yes. Are the accelerations of the two equal?
that would,
Why not?
they have different masses.
Okay, so what about the cannon's acceleration?
The cannon's acceleration, it doesn't accelerate very much
Because?
because its mass is so much more.
Right, and so Newton's second law, right? Newton's second law, everybody get that? I saw humans are unbelievable sometimes what we build. I'm not going to talk about the Hadron Collider. That's unbelievable. We built something like that. The most expensive, biggest instrument we've ever used is used to see the smallest objects that we ever had thought about. But we built some cannons in our history, and some of these cannons are unreal how big they are. They shoot miles, like 5 miles. Can you imagine shooting something 5 miles, a cannon? And anyway, some of these cannons there's so much recoil. There was so much recoil, they put them on like railroad tracks with springs. And anyways, they were huge, huge cannons, but they still had so much recoil that they would come back. Okay, let's go to the next one, 9. Marie, when a cannon is fired, why? Oh, we already answered that question. Now just do 10. Identify the force that propels a rocket.
Gas inside the rocket pushing on the walls of the rocket.
The gas is inside the combustion chamber, push on the combustion chamber, and then what?
Combustion chamber pushes on the rocket.
That's right. And the most important part of the rocket is the hole. Without the hole, you don't have a net force. You have net force actually in the direction. So the net force is to force the gases toward the opening. And the net force on the combustion chamber is to force the combustion chamber away from the opening, like that. All right, next one. How does a helicopter get its lifting force?
The blades of the helicopter push air down and there's an upward reaction.
That's right. I don't know if you ever thought about that. How about when you're in a kayak, right? Why do I do that? Why do I do that? I push water which way? Well, what's that going to do? It's going to push me forward, isn't it? And it's going to push that paddle forward, and I hang on to the paddle, so it pushes me forward, doesn't it? Okay. Let's see. 12. True or false? When a net force is exerted on a system, the system will accelerate. But when applied force and its reaction are within the system as a whole does not accelerate. Wow, that's a complicated question. That is true. So, for example, let's watch this. The horse pulls on the cart, right? And the cart pulls on the horse. I want to go back to that. Let's see this picture here. The other class, I don't know why, they had a little trouble with this. And I don't think you're going to have any trouble. So let's see if you can answer this one. Ryan, you're next. Ryan, how many forces, can you see the picture at all from back there? How about now? How many forces are acting on the cart? Yep. Now, the cart will accelerate to the right if blank is greater than blank. All right, fill in the blanks. The cart will accelerate to the right if blank is greater than blank.
F1 is greater than F2.
Okay? What are the two forces on the cart again?
Oh, shoot, no, if, B2 is bigger than F2.
Little f2, right?
Yeah.
Now, so that will tell me if the cart is going to accelerate, because that'll be a net force to the right, won't it? All right, let's try another one. Back up here, Mason. How many forces acting on the horse?
2.
The horse will accelerate to the right if blank is greater than blank.
F1 is greater than P, or big F1 is greater than P1.
Yes. That's very good. Everybody get that? Next one, Avery. Now I want to think of the horse and the cart as one object, one system, not two. How many forces the horse and the cart are going to accelerate to the right if blank is greater than blank? Go ahead.
Big F2 is bigger.
I'll give you a clue. Big F2 is not on the horse cart. And I wouldn't look at little f1 either. When will the horse cart accelerate to the right? I'll give you a clue. You have to have a net force to the right to accelerate the horse cart.
Big F1 is bigger than little F2.
Yes, that's exactly right. Okay, just a minute. Hello. Okay. All right. She's in the bathroom. Becca. She's going to sign out. Is she not feeling well? Can somebody? Can you go see if you can find Becca? Okay, maybe you don't want to do that. She said she was going to go to the restroom, but they want her to sign out. So, what now?
She's gonna go to the
Oh, I thought she said she had to go to the restroom. Oh, okay, sorry. Oh, okay, sorry. All right, anyway, that was actually the answer to the horse cart problem is, and I'll show you one more example, and I've done this twice now, but I'll do it again. Right now, I can push on the chair. I can feel it. I'm pushing the chair that way, and the chair is pushing my hand that way. But what's happening is nobody's accelerating anything. Because really, me and the chair are part of the same system now, and so those forces are called internal forces, and they can't affect acceleration at all. But what if the horse cart system interacts now with the ground? Then I can push the ground that way, and it can push the horse cart system that way. All right, I'm going to be here today after school, and he said, well, that wasn't a bad review, but I wouldn't mind doing that, and I'll be here tomorrow morning also. So that's about it. All right, thank you very much.